Hello again. So today what we're going to do is we're going to start our next unit on triangles. We're going to start off by classifying them, right? Trying to figure out what we can name them based on different criteria. So first off, we're going to talk about what a polygon is. A polygon is really just a shape, but specifically it's a shape made up of just straight lines. Right? So like a circle is not a type of polygon. If I had like a kind of like a half pizza shape or just like a, oops, that's not quite what I was going for. If I had a shape like that, that is not a polygon because it has that curved side. Right? A triangle is specifically just a polygon with, you probably guessed it, 3 sides. Right? You need to have 3 straight lines that make up a triangle. We have the sides, right? The sides are the line segments that make up a polygon. Right? So, obviously we have sides of a shape, right? It's just what you would think it is. What you might not have run into before are these things called vertices, right? We're going to be talking about vertices and the singular, right? If you're talking about just one of them, it's called a vertex. These are kind of like the corners of a polygon, and I have it in quotation marks because if you think about it, you think of a corner as like, oh yeah, you've got 2 walls meeting 90 degrees, that's a corner, right? But when I'm saying corners in quotation marks there, it's just where the sides meet, right, or intersect, right? So whenever you have 2 sides that kind of meet at a spot, that is a vertex of that polygon, right? Now we can finally talk about the different types of triangles, right? So we've got 2 different groups here, right? We've got these 3 that are all going to be talking about angles, and then we've got these other 3 where we're going to be talking about the sides, right? So if that's helpful, if off to the side of this you wanted to write out angles, oops, and I know that's a little bit messy, it's on the side of my screen. And we got sides for those ones, right? So as far as the angles go, right, when we're talking about acute triangle, we are talking about a triangle with all 3 of the angles measuring less than 90 degrees, right? They're all tiny angles, right? An example of an acute triangle might look something like that, right? None of those angles on the inside, right? If I'm looking at, these 3 tiny little angles in there, none of those are bigger than 90 or even equal to 90. Right? We're talking about a right triangle. It's a triangle with one angle measuring exactly 90 degrees. Right? So a triangle that's a right triangle might look something like that. Right? It's got that one, specifically one right angle moving around in it. Let me fix this up a little bit. Oh wow, it's real mad at me today. That's okay. Right, we got that one right angle in there. And then we've got an obtuse triangle, right? This is a triangle with one angle measuring more than 90 degrees, right? So these ones you may not have run into too much in the past, right? But you can kind of imagine it. It's just a triangle that might look something like that, right? It's got this one big angle right in there that is bigger than 90 degrees, right? So it's kind of elongated like that. So we can name them by the types of angles they have. We can also give triangles another name based on how the sides work out. So when we're talking about the sides, right, we have one called a scalene triangle. That's when we have a triangle with 3 sides of different lengths. Right? So if we have a triangle where none of the sides are the same length, right? So kind of like, say something like this. Oops. Let's try that last line one more time. There we go, right? None of those sides are the same length, right? If I was putting little markers in, none of those have the same length to them, right? So we'd call that a scalene triangle. An isosceles triangle you may have heard of before, that is a triangle with at least 2 equal sides, right? So a scalene or an isosceles triangle might look something like this, right? Where it looks like these 2 sides that are kind of standing up appear to be the same size as one another, right? That last one is just kind of hanging out. It's doing its own thing. As far as an equilateral triangle goes, this is a triangle with 3 sides of all equal length, right? So kind of like that first triangle I drew up where it says acute triangle, right? If all 3 sides are about the same, let's see if I can get it to snap together nicely, right? If all 3 sides are the same length, more or less kind of like that, right, then we have an equilateral triangle, right? Equal meaning equal, lateral talking about side length, all right? So what we're going to do is we're just going to classify a couple things, right? We're going to classify the triangles based on these, vertices that they're mentioning as acute, equilateral, obtuse, or right, right? So JMN, right, let's take a look at that one first. So JMN is this big triangle here, right? I'm just going from one vertex to the other and then kind of connecting it all together. If I'm looking at that one, it does not appear to be an acute triangle, right, because of that angle down by N, right? It doesn't seem to be equilateral. Those sides seem to be of different lengths. It seems like it could be obtuse though, right? That angle down by N looks like it's bigger than 90 degrees. That's all we need to know in order to call this an obtuse triangle. All right, cool. So that part's done. Let's move on to another one. If I'm looking at OLN, right, that triangle right there, seems like all the angles are less than 90 degrees, right? So we could call that an acute triangle. Oops. And then we're also going to take a look and say, like, all right, those sides also look like they're about the same length, right? So we can also call that equilateral. Right? So we can do both, right? You can give it more than one name as long as it matches up with the right criteria, right? What about JKO, right? So take a second, take a look at JKO. See if you can come up with a name for that one. Might be a little tricky, right? But give it a go. Right? Hopefully you came up with the same thing that I'm thinking. What I'm seeing, and you might have called this obtuse, right, depending on how it looks on your paper, right? But what I'm seeing is that this angle over by K, where I'm kind of drawing it in, that looks like it's about a 90-degree angle, right? So I would do that as I would call that a right triangle, right? I could see the argument being made that it's either obtuse or acute, right? It all really depends on how big this angle is by K, right? If this angle in here was less than 90 degrees, I could see it being acute. If it was slightly bigger than 90 degrees, it would be obtuse, right? So it all really depends on how big that is. All right, we've also got OKL, right? If I'm looking at that one, right, again, it really just depends on what this angle is doing over here, right? Oops. If that angle is a right angle, right, then we have a right triangle. If it's bigger than 90, it's obtuse. If it's smaller, same deal as the last one. I'm going to go ahead and say that that one is also a right triangle. Ooh, my goodness. Things not taking my handwriting very well today, so please excuse that. Hooey. Right? Let's try something out a little bit different. Right? We've got this other diagram here. I want to name as many isosceles triangles as we can find in this diagram. Right? So isosceles just means that they have to have two sides that are the same length. So what I'm seeing is like these markings that I'm putting in yellow, these markings that I'm putting in blue, right? Those are telling me that those are equally lengthed sides, equal measured sides, right? So what I'm seeing is that the triangle made up of those yellow pieces, right? I'm going to do it in green, I guess. Right? So those two sides plus whatever side is kind of in between, right? That is going to be an isosceles triangle. Right? So when we're naming a triangle, we need to name it by the three vertices, right? I'm also going to put this triangle symbol out in front of it. So when I'm naming that one that's in green right there, I'm just going to call it triangle ADB, right? You could call it ABD or DBA or BDA or whatever, right? As long as you're going around the triangle, naming all those vertices, right? So then if I'm also taking a look at what's going on with those markings in blue, that is another isosceles triangle, right? I've got these two sides that match up, and then this other side that runs between them, which gives me that other triangle there. So another isosceles triangle, right, would be triangle BED, right? Making me tired, going to bed, right? So again, we're just naming isosceles triangles. They have to have two sides of the same length. Oh, scalene triangles. So there's a lot of options here. The only thing that we really need to have in order for it to be scalene is that the sides have to be different lengths from one another. All three of them, right? None of them can match. So what I'm seeing is if I went like this, that's one length worth of side. This is a different side length, and then that third one along the side there. that would be a nice scalene triangle right away. Right, so we have triangle BAC. Right, you might also be seeing, if I just kind of flip-flop it, look at the other side of that, we could have triangle ACD. Right, so there are actually, I found 6. You could maybe find another one if you're thinking a little outside the box here, but if we can find triangles that have all 3 sides of different lengths, then we can use it as a scalene triangle. You can actually even go, from A to E, E to D, and D to A. None of those are going to be the same length, right? So you have triangle AED. Right? You could also flip-flop it. You could have angle ABE. Just over on the other side, right? Flip it right over. Right? The last little set of triangles that we could find in here that are scalene, that I found at least, are these ones here, these 2 little tiny ones down on the bottom. So you have angle CDE. Oop, I keep saying angle. Triangle CDE and triangle BCE. Right? If you're worried, like, oh my God, how am I supposed to be able to figure out how many of them there are, right? It's not about finding every single last one, right? It's about knowing what we're looking for, right? So isosceles, we had to find 2 side lengths that were the same. When we're talking about scalene, we need them to all be different, right? So if you can find a couple, that's all we're really going for, right? Don't stress out too much. Right? So this one's a little bit more complex. Right? What I'd like you to do is take a quick second, see if you can come up with an isosceles triangle, see if you can come up with a scalene triangle, right? See if you can actually figure out, call it, actually, I'll give you a goal. See if you can find 1 isosceles and 3 scalene triangles, right? So pause here, give that a shot. So hopefully you gave that a go, right? Let's see how we can do, right? If I'm looking for isosceles triangles, the easy one to find is just where it mentions that they have the same side length, right there and right there, right? So what I'm going to have is I have triangle UTX. Right? And that's it. Right? That's all I really find for isosceles. You could also, you could argue that UVX here is also isosceles. Right? It seems like those sides are all the same length. That one's a little bit of a stretch, right? But if you wrote that one down, I probably would mark it right as well, UVX. Right? But when we're looking for isosceles triangles, it's really helpful if, like I have there in the yellow, we know that they're the same because they have that measurement on them, right? They have that little tick mark showing us that they're the same. Excuse me. So as far as scalene triangles, it's really up to you, You can find any number of scalene triangles here. We could find this kind of like skinny one there. We could be talking about something like this one off to the side there, because again, it doesn't have that measurement telling me it's the same, right? I could even find, one of these, oops, let's not use the same colors over and over. Could even find something even kind of skinnier and longer like that, right? Any of these would be good scalene triangles, right? So I have a list of ones that I found before. I'm just going to write them out. Could have triangle VYX. Could have triangle ZTX. Could have triangle VZU. Could have triangle YTU. Triangle VWX. Triangle ZUX. And triangle YXU. Right? Those are all the ones that I found. You may have found even another one that's scalene, right? There's a lot of different options there, right? But again, don't stress about finding every single one. We just want to be able to know what we're looking for and maybe name 1 or 2, all right? So last little bit that we have to talk about today is where, the more traditional kind of math comes in, right? We're going to do a little bit of algebra to help us figure some things out. So we want to find x and the measure of each side of this equilateral triangle we have, right? So what's important here is to note that they tell us that this is an equilateral triangle, right? Because it's equilateral, that means that all the sides are equal to each other, right? So that means that everything I'm going to highlight here in yellow, x plus 9 is equal to 2x, right? It's also equal to 3x minus 9. Right? All 3 of those things are equal to each other. So the way that I'm going to approach this problem is because they are equal to each other, I'm going to set them equal to each other, right? I'm going to say x plus 9 is equal to 2x. That's going to set me up with an equation that's not too bad to solve, right? To solve this out, right, I just need to get the x's all on their own side and all the numbers on the other side. I'm going to subtract an x to get it away from that left side there. I'm going to get that 9 is equal to x. Cool. We found out what x is, right? That's really all we had to do. After that, now that we know that the x is 9, I'm just going to plug that back in to see what all these sides are going to be, right? So, you may have run into problems like this in the past where they kind of like check themselves as you finish it up, right? Because this is an equilateral triangle, if my 9 is correct, all of these should come out to be the same, all these things in yellow, right? So let's take a look at ST right there. If I plug a 9 in for that x, that's 2 times 9, that's going to land me with 18 here, right? If I look over here with SR, right, if I plug a 9 in for x, 9 plus 9 is also 18. Cool. Last one down there, if I look at RT, 3x minus 9, right? So 3 times 9 minus 9, right? If I'm simplifying that down, right, 3 times 9 is 27. Oh, gosh. Minus 9, right? 27 minus 9 is going to give us 18, right? So again, it checked our work for us in a way, right? We found out that they are all the same, which is exactly what we were hoping for, right? Let's try another one of these out, right? We want to find D and the measure of each side of triangle KLM if it is equilateral, and KL is that, LM is that, and KM is the third one there. So they don't give us a diagram on this one, but what I would suggest the first thing to do is draw out a diagram for yourself, right? So we know that it is an equilateral triangle. So what I want to do is try and draw something where all three sides appear to be around the same length, right? And I know that you don't have a fancy like snap to shape thing and all that on your paper, but try and get it, relatively close to that because it's easier to visualize. I know that it's equilateral, so I know it's going to be the same measure on each of these three sides, right? So just like the last one, all of these pieces are going to be equal to each other. It's triangle KLM. Right. KL is D plus 2, right? So let's pop that in there. LM is 12 minus D. And KM is 4D minus 13, right? So similar to the last one, right? It's equilateral. All three of these pieces that I'm going to highlight here in just a second are equal to each other, right? So again, when you're faced with a problem like this, we're going to set them up in an equation. I'm going to choose the two easiest ones to work with, right? And the easiest ones to work with are just the simplest looking ones, right? There's not really any great mathematical secret about it. So what I'm going to do is I'm going to use D plus 2 and 12 minus D, and that'll probably be easier than working with 4D minus 13. So D plus 2 is one side of this, right? I know that D plus 2 is going to have to be equal to 12 minus D, right? To solve this out, all I have to do is get all the D's to one side and all the other numbers to the other side. All right, so what I'm going to do is I'm going to add D over here to cancel it out from the right-hand side. I got to do the same thing on the left to keep everything nice and even. So it's going to be 2D plus 2 equals 12. All right. After that, in order to get those D's by themselves, I need to move that 2 over. So I'm going to have to subtract 2 to cancel it out from over there. All right. So now we've got 2D is equal to 10. One last step, right? Don't forget that 2D is 2 times D. So to undo that 2, we need to divide by 2, right? Doing the opposite of that multiplication that's there. It's going to help us cancel out the 2's. We're going to get that D is equal to 5. All right, and again, hopefully excuse the bad handwriting. Still fighting me every single letter. All right, so D is equal to 5. All right. Our last thing we got to do is just triple double check it, make sure that it's going to come out the same on each one of those sides when we figure out their lengths. So what I'm going to do is I'm going to take a look over here at KL, right? D plus 2. right? So 5 plus 2 is going to give me 7, right? LM along the bottom is 12 minus D, so 12 minus 5 is also going to give me 7, right? Last one, from K to M, right over here on the right, 4D minus 13. So 4D, so 4 times that 5 minus 13. Well, 4 times 5 is 20, and 20 minus 13 is 7, right? So we found out that it was 7 on each and every one of those, right? So again, when you're doing these problems, they check themselves when you're getting your final answer. If I ended up with 7, 7, and let's say that this one came out as like, oh yeah, that's 12, right? Not correct, right? We know that we did something wrong somewhere along the way and we got to check it, right? If we came up with the same thing though, just like we did on the last one as well, then we know that we're all set because it had to be equilateral. They all had to be the same, right? So that's actually it for this one. I know I've been talking probably a little bit more than I needed to, but here we are. And I'm going to say goodbye for now. Peace out.